Dear students, question number 31 says that if alpha and beta are the apparent angles of dip in two vertical planes at right angles to each other at a place where del is the true angle of dip, then the four options are given. First is cos square del is equal to cos square alpha plus cos square beta. Second option, cot square del is equal to cot square alpha plus cot square beta. The third option, which says that cot square alpha is equal to cot square beta plus cot square del, or the fourth option, which is tan square del is equal to tan square alpha plus tan square beta. Dear students, if a plane makes an angle phi with the magnetic meridian and the apparent angle of dip in that plane is del dash, then it can be related to true angle of dip, which is called del, by the following relation, that tan of del dash, where del dash is the apparent angle of dip, is equal to tan of del, where del is the true angle of dip, divided by cos phi. Here phi is the angle made by the plane with the magnetic meridian. Herein, let us assume that one plane makes an angle phi. Since the next plane is at angle of 90 degree with the first plane, the next plane must make an angle of 90 minus phi with the magnetic meridian. So using this information, we can write that tan alpha, which is the apparent angle of dip in the first plane, is equal to tan del divided by cos phi, and tan beta is equal to tan del divided by cos 90 minus phi, which can also be written as tan del divided by sin phi. Now dear students, if we simplify these two equations, from the first equation we can get that cos of phi is equal to tan del divided by tan alpha, and from the second equation we can get that sin phi is equal to tan del divided by tan beta. Now dear students, we know that sin square phi plus cos square phi must be equal to 1, which means that tan square del by tan square alpha plus tan square del by tan square beta should be equal to 1. Now dear students, simplifying this equation, we can easily get that cot square alpha plus cot square beta is equal to cot square del. Therefore dear students, the correct answer for this particular question should be option number 2. Now let us proceed to the next question, which is question number 32. Dear students, question number 32 says that a uniform magnetic field that exists in space is given as B vector is equal to 2y cap plus 4j cap Tesla. The magnetic flux through an area of 1 meter square lying in XY plane will be. Now dear students, we know that the magnetic flux can be written as B vector dot A vector, where A vector is the area vector. Herein the area vector has a magnitude of 1 meter square and it lies in XY plane. Therefore area vector can be written to be equal to 1 k cap. Substituting the given values to calculate the magnetic flux, we can proceed and write that the magnetic field is equal to 2y cap plus 4j cap dot 1 k cap. Dear students, the flux therefore would be equal to 0, as the dot product of these two vectors is equal to 0. So the correct answer for this particular question should be option number 4. Now let us proceed to the question number 33. Question number 33 says that a rectangular loop ABCD having some resistance is pulled with constant velocity v out of the uniform magnetic field directed into the plane of paper. At t is equal to 0, side BC of the loop is at edge of the magnetic field as shown in the figure. the induced current I versus time t graph will be. Now dear students, this is a question on the concept of motional EMF. Herein, as the loop comes out of the magnetic field, a motional EMF in this side of the loop will be created. Now the motional EMF's value would be equal to BV multiplied by the length of this side, which is small b. And since the resistance of this particular loop has been given to us, the current can be written as BVB by resistance of the loop. Let us assume that the resistance is R. So dear students, we can see that the current which is flowing in the loop is a constant value, as the velocity is constant, magnetic field is constant, B and R are also constant. One thing that needs to be acknowledged is as the loop leaves the magnetic field completely, the motional EMF in the loop becomes zero and the current as well reduces to zero. Therefore, initially the current is constant and suddenly becomes zero. The only graph which represents this variation perfectly or in the best possible way is the graph as per option number 1, and therefore that should be our correct option. Let us proceed to the question number 34 now. Question number 34 says that the magnetic flux linked with the stationary loop of resistance R varies with respect to time during the time interval t is equal to 0 to t is equal to capital T as phi is equal to 2t bracket capital T minus small t. The amount of heat generated in the loop during that time is, we have to assume that the inductance of the coil is negligible. Now dear students, the flux has been given to us to be equal to 2t capital T minus small t, which can also be written as 2 small t capital T minus 2 t square. Now dear students, we can find out the magnitude of the induced EMF in the loop, which is equal to d phi by dt. Differentiating the equation of phi, we get d phi by dt to be equal to 2 capital T minus 4t. Now dear students, the power dissipated through a resistor can be written as E square by R, which is equal to 2 capital T minus 4 small t square divided by R. The heat can be calculated as an integral of power dt, which will be equal to 2 capital T minus 4 small t square by R, integral of it with respect to dt. The limits will be from 0 to capital T as given in the question. Now dear students, to calculate the integration of this, we can expand it using the formula of a plus b to the power 2. We get 4 capital T square plus 16 t square minus 16 small t capital T dt divided by R. Dear students, on solving this integral, we get a value of 4 t cube by 3R. So the correct answer therefore is option number 3. Now let us proceed to the question number 35. Dear students, question number 35 says that the equivalent inductance of two inductors is 4.8 millihenry when connected in parallel and 20 millihenry when connected in series. The value of inductance of individual inductors are. Neglect mutual inductance. Now dear students, the equivalent inductance in series combination can be written as L1 plus L2, where L1 and L2 are individual inductances, while in parallel combination the inductance can be written as L1 multiplied by L2 divided by L1 plus L2. Now L1 plus L2, that is the series combination, has been given to us to be equal to 20 millihenry as per the question, while in the parallel combination the value of the net inductance has been given to us as 4.8 millihenry. Substituting the value of L1 plus L2 here, we can write that L1 multiplied by L2 is equal to 20 into 4.8, which can also be written as 96. Now dear students, we have two equations and two variables wherein we need to solve and find out the values of individual variables. For that, we can write that L1 minus L2 to the power 2, that is square, is equal to L1 plus L2 square minus 4L1 L2, which can be written as 20 square minus 4 into 96, which will be equal to 16 millihenry. Therefore, L1 minus L2 is equal to 4 millihenry. Let us label this equation as equation 1 and this equation as equation 2. If we add equation 1 and equation 2, we get that 2L1 is equal to 24, which means that L1 is equal to 12 millihenry. And further, L2 can be calculated to be equal to 8 millihenry. Therefore, dear students, the correct answer for this particular question should be option number 1. Now let us proceed to the further question, which is question number 36.